Okay, we're going to go through, and I have some guest lecturers here, but we're going to go through basically all the calculator programs pretty quickly so you can just see where there might be issues. And I'm not going to go through the menu part. I'm going to go through the direct program, except where one program references the other. So that's typically in the vector thing. You know, there's about 4 or 5 programs which reference each other. They would be called subroutines. They can be called subprograms, but we're going to go straight through right down the whole menu list. And of course, you have to remember to turn on the calculator. And you notice right there, it kind of remembered that it was, you know, it's got an issue there. I'm going to hit break. I'm going to hit clear. And somehow this thing, when I left it going, it was in the middle of a routine. So I'm going to start here with AAA. I have no idea what it is. I'm going to just hit it. And AAA, somehow, look, I got an error undefined, like it had an issue when it tried to do something. So what will get you this error? I don't know. You can look in Program, Edit, AAA, and somehow down in this program, it was trying to do something it didn't want to do. All right, it probably tried to write text in string 1 and from string 1 and string 2 that did not exist. There's nothing in that string 1 and string 2. So that's an example of looking down and thinking, okay, now I'm going to go second quit here, and we're going to erase all that stuff out soon. Where do I look at my variables? I'm going to look at my variables by going to vars and then going down to my string variables, right? Knowing where are your variables, and string 1 doesn't have anything in it, right? So let me do this just to show you that, you know, don't completely freak out when programs don't work. I'm going to just take here second quotes alpha A. Oh, now you freak out. Second quit alpha A, and I'm just going to go alpha A. I'm going to store it into variable string 1, right? That put it in string 1, and now I can say variable string 1 and put that into variable string 2. Now, here's what you realize. This is why you learn to do this on a computer. And you learn, you know, what's the capitalization, what's not, because it's a lot easier to do. And so what I've done now is I've just put A into letters string A1 and string 2. Now if I hit my program again, the first one that just is floating around on my calculator, hit that, it does everything, and it put the text where I told it. And it always is going to graph what you've got set up in your graphs. So no matter what, if you've got functions in your calculator that are going to graph, or in this case, a stat graph, it's going to always show that first on your graphics screen. So that's a reason why, for the most part, I'm going to hit second stat plot here. Keep them off unless you want them on. So in other words, you keep, you know, your machine set a certain way that it's not doing stuff you don't want it to do. I guess an example in Civil 3D would be having your recalc on your corridors not set to automatic. So these kind of things are these settings. So I'm going to hit that second quit, and I'm going to try it one more time. If you think about it, I have variable data in there, obviously. Now it's, as I'm going to do it one more time, I'm going to go program AAA. There he goes. It does the graph because I also have a function in there that's graphing. Now that's not so bad, but I can go y equals, and there's that function that I have floating around because of the flow graph thing, right? It's not such a hard function to keep bare, right? And so you'll see later, it's a nice idea actually to keep these things clear and then put them in as they need be. All right, so now when I hit second quit and I go to program, right, and I go to AAA, run it, I get what I wanted, I guess, which is a couple of lines here because I've got the graph on, whatever else. I'm going to point out there's a couple other things here. It's hard to read, and this here second format, right, whether or not your coordinates on, like for now I have my axes on, I want my axes off, right, that's on the graph screen. I want rectangular or polar coordinates, I got all these different things, so there's more settings up here that have to do with graphs going across the top. That's why you probably might use these in math. but I'm going to hit now, say second quit. Once again, run my program, and this time I won't even see anything. I guess it's still got a line floating up and down here, but that was the vertical line. All right, so that's you know, that's a program that I'm not even using, but that's there so you can learn to troubleshoot, and mostly it's there because I didn't erase it. All right, next one. I'm just going to do these in order. Bernoullis. We'll come back to them in some context. But Bernoullis, right, it has a rev date of 11:02. If you do not have a rev date of 11:02 on your calculator, make a note and make sure you update them in the morning. Of course, because I know you're listening to it this weekend because I sent you an email. I hit that. This is generally, Bernoullis equation is used lots of different places, but this Bernoullis equation is for a free-flowing pipe system for the most part. In other words, if you know the length of the pipe and the friction factor based on Moody's, what will be the flow of the pipe, the Reynolds number, and everything else. You remember we use this if we need to iterate to get a final solution. If in fact you know the relative roughness of the pipe, in other words, you know what the type of pipe it is, so you know how much internal topography it is, and you know the diameter, you can know absolutely what the friction factor is by going to Moody's diagram. So in this case, let's say the length was 2,000 feet of the pipe. The diameter, I'm going to make it a 6-inch pipe, 0.5 feet. You know, at least I've got some input there, which is being correct. The friction factor, I'm just going to guess 1.01 right now. You would look it up because you would have gone and looked at what the relative roughness was. This formula is not going to, this calculator is not going to do that for you. You need to look at it. What is the material? I think the one we know offhand is cast is like 0.00085. You have to divide that by the diameter to get the relative roughness. You look at the flat spot on the Moody diagram and it gives you a friction factor. You have the head, meaning in this case the distance or the difference between the piezometric head at the start and the elevation, or the elevation of the center of the pipe. Usually the piezometric head is the same as the elevation in a reservoir. Unless, of course, you've got an extra 60 psi pushing on your pressure tank, then you have an additional feet of head that is added to your beginning spot. But for the rule, we're doing open reservoir problems. You take that H as being the elevation from the reservoir to the middle of the pipe at exit. You hit a head, and I'll say in this case it's 2,000 feet. Let's say it's just falling 20. It tells me at this point an answer of how much flow will be flowing, what the velocity head is, 0.487. So that's the amount of energy that the energy grade line has above the exit. In other words, it has 5.6 feet per second is the velocity. That squared divided by 2g is 0.48. So you'll see very often these energy grade lines look like they go almost right through the center of the pipe. If you remember, this is a 6-inch diameter pipe. And so this is actually what? About 3 inches above the energy gray line is only 3 inches above the top of the pipe because you're always going to the center of the pipe. But you write these things down. You know that it's 5.6. You know that the friction factor is 0.01. And you know that when you finally graph this, it should actually go through 2,000 feet down the pipeline. It should go through a spot that's a little bit higher than 20, or I'm sorry, higher than 180. So I'm going to see if I can turn that back on, and we're going to try to, I'm going to quit. Who knows what it did. I'm going to hit clear. So now I'm going to jump real quick. I'm running out in 20 minutes to the graph one, 20 seconds. I'm going to go to program and then go down to flow graph. Hit flow graph, and it's got a rev date of 11:02. I'm not going to set this up, though you see what you're supposed to do. My F from Moody was 0.01, correct? My velocity was 5.6. My diameter was 0.5. And my elevation at the start, let's just assume it was 200 tall. and my length down the pipe in this case is 2,000, and I enter here, and if you notice, that's almost exactly what I said it was. It's about just a little bit above the center of the pipe. That's it for those. We'll catch you on the next video.